Hello, everyone. Welcome to my data structure tutorial. Here's my welcome page. This is going over the three data structures that I chose for this assignment, and then just contact information. Let's go ahead and start with the first one. We got stacks. Stack, basically just a list. An important thing to note is that it's using LIFO, last in, first out. The reason that's important is because with that information, you're able to determine if you're adding something or removing something, where that's coming from. Here are some basic functions for the stack. We got the append to add a value to the back of the stack. Value, the pop, this is going to remove it, remove the last one that was added. You can find the length of a stack using length. You can also check if the stack is empty, which will come in handy sometimes. Here's an example I came up with where you fold your clothes, but you're looking through them through a stack of clothes, and you got to keep on looking until you find the stack or the clothing item that you're looking for. The problem I came up with was grading tests. Basically, you have students that turned in some tests, and you have to assign them a grade. But you have to grade the tests. You can go ahead and look at the solution to that here. Adding test to a pile, grading the test, assigning it a random integer between 50 and 100. Here are the people's test that we are testing. Here you can see it running. As you can see, the first one to go is Bob because he is the last one in the stack. So he's the first one to get graded. Or in this example, he's at the top of the pile of tests, or the last one to turn in his test. So there's that example. Let's go ahead back to the welcome page. The next thing I chose was sets. Sets are a very cool data structure, actually, because the way they store data, there's no set order, which is very unique for them. Because there's no set order, you're not allowed to have duplicates, because where they're storing that data is the value that they are given. So a 3 is stored in 3. With that, to be able to store strings, letters, characters, whatever, you have to use hashing, which, as you can see here, my name 3 is hashed to 3, but my name is hashed to whatever number that is, and it's stored in that spot. This allows you to access data really fast, and that's always great when you're dealing with large sets of data. Here are some common set operators. We got the add value, adds it to the set. You can remove from the set. You can also check if a value is in the set, and you can check the length of a set as well. In the example section, I have 2 sets, Python, dictionaries, whatever you want to call them. And you can use intersection, which will display similar things between 2 sets, and union displays the difference between 2 sets. Or the other way around, I think. Yeah. Intersection displays what's similar. Union displays what's unique between the two sets or what's different. The problem I came up with was a restaurant problem. Basically, you have a restaurant that can only hold 10 people. You have to call ahead, and if you're not on the list when you show up, you obviously can't be seated. Here's the solution to that. We're checking the list. You have to use upper. That's that. Go ahead and run it. As you can see, you can add names. John, Jake. And anyways, you add the names and then you check the names if they're on the list, basically. And check if I'm on the list. If I am, or the restaurant, Tom's on the list. If I put like T, I'm not on the list. And finally, we have the trees, which is a very fun data structure. Similar to linked lists, they have pointers, but they can connect. You have binary connect to more nodes. You have binary trees, which just means that they're not connected to no more than two nodes. Like here, you couldn't connect to a third. This is because, I mean, you have 0 and 1 is how it's separated, 0, 1, 0, 1. There would be a 0 there and then a 1. A binary search tree, it allows you to put data into it. Basically, if it's less than, it will go to the left subtree. If it's greater than, it goes to the right subtree. You can see this with the root being 13. 15 is greater than 13, so it goes to the right. 20 is greater, it goes right, right. 10 is less than, it goes 10. But when we're adding 11, it's less than 13, greater than 10, so it goes right. And same with 5, less than 13, less than 10, so it goes to the left. Here we can see an unbalanced tree. This is faster to add things because you're not comparing them, but you have to have it in numerical order and add the smallest to the largest to be able to get this. Most of the time we don't want that. We want a balanced tree or a BST. A balanced binary search tree is just it depends on the tree. The AVL tree, you can't have anything more than a 2 height difference. So here you have 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is a balanced tree. As you can see there, I mean, you have 1, 2 there, but it's not greater than 2, so you're good there. You have the operations, inserting a node, traversing a node. They deal with recursion. They're pretty complex. It's worse if it's a balanced tree. You have to make sure that the tree continues to stay balanced as you're inserting a node. Problem I came up with this, I just used a template from an assignment we did, from the assignment I finished. And then basically I'm just having them create the contains function. And so this is what it's, this is what we're getting with that. We're putting things into the tree and then we're checking if these are in the tree or not. And with that, that is everything. Thanks for watching.